Let's get started on factorial notation. So, as you may have seen in math before, factorial notation is often described as being this, an exclamation point. So, if you ever want to say it, you can say it as this. Like, if you have an exclamation point, that's described as being n factorial. That's how you say it. Now, what does that mean, you might ask? So, for n is all integers, n is greater than 1, n factorial is the product of the first n positive integers. That might sound weird, but let me make it a little less confusing. So let's express n factorial as this. N factorial is equal to this. N times n minus 1 times n minus 2, so on and so forth. Minus 3, minus 4, minus 5, minus 6, and so on. Until you eventually reach 3 times 2 times 1, right? And that's how we express factorial.
So, people of YouTube, you may be thinking, how does this work in practice? What do all of these little variables actually mean? Well, I am here to show you. So, what does 8 factorial equal? Now, pause the video if you know what this equals, but I'm going to show you now. So, what it equals is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, what does, for example, 2 factorial equal? 2 factorial equals 2 times 1, in other words, 2. Okay, so.
Now let's think about 8 factorial for a second, guys. How can we express this differently? Pause and think about it.
Well, you can express this differently because 8 factorial is equal to 8 times, notice this bit here. What does that mean? Well, that actually means 7 factorial. So, what this means is, yeah, that's how you express it. And so you may be thinking, okay, is this the case for all positive integers? Well, actually, 0 factorial does not equal 0. You may be thinking, okay, why is that the case? Well, I'm here to show you. This is the case because here's a mini proof to show that this is the case. So what you have effectively is, for instance, 6 factorial is equal to 7 factorial over 7. Now this statement is true because 7 factorial, in other words, is just 7 times 6 factorial.
As we proved previously.
Exactly.
Divided by 7.
Divided by 7. And then you cross these two out because this is just 7 divided by 7, which is equal to 1. And then you get your 6 factorial over 1, which is equal to 6 factorial. So that statement is correct. Now, you can go down. You can be like, okay, if that's true, then this must also mean that 2 factorial is equal to 3 factorial over 3, which is true. Now, you might also be thinking 1 factorial is equal to 2 factorial over 2, which is also true. Now, 0 factorial is equal to 1 factorial over 1. Now, 1 factorial means 1 times 1 over 1 means 1. That is the proof to show that 0 factorial is actually equal to 1, not 0.
And while you may not be asked on tests specifically to prove this, it is still an important fact to know because as you guys get into binomial theorem, 0 factorial becomes increasingly important, and you increasingly need to know that 0 factorial is equal to 1. You also can find this using your calculator. In your button, in your calculator, you can oftentimes find that 0 factorial is 1. So, yeah. If you had to suffer the same way we did in IB, you are likely here too. And if you don't want to waste hours of your life, like we did, having to expand binomials by hand, then skip. But if you want to watch how we had to suffer, here we are.
So, if you do not want to do this, then utilize something called Pascal's triangle. So, Pascal's triangle. So, what Pascal's triangle is, well, first of all, Pascal was this dude from the West, and he was like, right, let us save these people's misery and let them
Expand binomials efficiently.
Exactly. Let them expand binomials in an efficient and concise manner that does not make you not enjoy mathematics. So, what Pascal said was right. We have a 1 here, okay? These are all the coefficients that you saw in the final answer there.
As you recall, my final solution, just for anyone who doesn't want to go back to the video and rewind it, looked something like this. It read as the following. A to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Now why is that relevant? We'll get to it.
Exactly. So Pascal's triangle. What Pascal said was right. Let's put a 1 there. Let's put another 2 1s there. Now, what he noticed was, let's find the sum of these, and then you get 2, okay? And then you always want to put your 1s on the outside. So you get 1, you get 1. The sum of 1 plus 2 is 3. And you always want to put your 1s on the outside. Then you get 3 plus 1, which is 4. 6, 4.
Now, ladies and gentlemen, does this look familiar from anywhere? Maybe to here? Wait a minute. Those are the same coefficients, are they not?
Exactly. All we're actually saying is this is the exact same coefficients as just mentioned in this example. This is a 1, this is a 4, this is a 6. No, sorry, this is a b, this is a 6, this is a 4, this is 1. So, it is present within final answer. Now, Pascal's triangle, you write this as the 0th row, you write this as the 1st row, write this as the 2nd row, you write this as the 3rd row, you write this one as the 4th row.
Now these are all very conveniently named as we just named them. It makes it very convenient to remember. If you want to go to the 4th power, take a wild guess what row you'll look into.
The 4th row. This specific beautiful row that we can see depicted here.
Now, how do we actually use this triangle?
So, let us utilize this triangle in writing out binomial expansion.
Now, just to keep all the methods the same, let's do this again, except without having to go through all the heartache of having to do the long way.
So, please remember that the coefficients were 1, 4, 6, 4, and 1. Bear that in mind when you are doing a binomial expansion with Pascal's triangle, because if you don't have that, you won't be able to do binomial expansion with Pascal's triangle. So, what you have is your a plus your b to the 4th. Now, instead of doing all that long, arduous process, you can actually just utilize the binomial expansion. So, what you can do is you can say, right, let us put the first coefficient in the front. Let's say 1, right? And then we call this x, and we call this b, sorry.
I wouldn't even name them.
Sorry.
I wouldn't even name them.
Sorry. We call this a, as it's presented, and we call this b. Now, you have a. What you want to find yourself doing in a binomial expansion is the n is, in this case, 4. So what that means is you want to find yourself going down by 1 every single time you multiply, which I'm going to now explain. So you have your 4 here, okay? Just bear in mind the process may be a bit complicated, but when you see
why we do this, we weren't explained in class. All you need to know is follow our definitions and our explanations and it'll work. So just follow along. Don't worry about why it works.
Don't worry about why it works.
It just does.
It's a smooth process. It's really beautiful once it works. It's very satisfying. Okay, b. Now, what you want to find yourself doing is each exponent has to add up to n, right? Each exponent has to add up to n. Okay, so what's 4 plus something equals 4? Well, 4 plus 0. Now, this whole thing adds to the next coefficient, which is a to the 3, because this goes down by 1, this goes up by 1. Now, this is like that, okay? And then it continues. 6 a to b2, or b squared, I should say. So, now, as you can see, this continues. So, plus 4, which is our next coefficient, times a to the exponent 1, b to the exponent of 3. And then finally, plus our last coefficient, which is 1, times a to the exponent of 0, b to the exponent of 4. Okay, so now, what does all of this mean? Well, something to the exponent of 0 is always going to be equal to 1. So you cancel these out. We don't want those, because something times 1 is always just the same thing. So we have 1.
And keep in mind, we are also multiplying a to the 4th times 1. So these things don't matter either. Let's just, for the sake of the doubt, take out the 1s too, because they do not matter.
They do not matter exactly. So we have a to the exponent 4 plus 4 times a to the exponent 3 times b, which can also be expressed as 4 times a to the 3b, plus, what does this say? Well, this says, or this means, 6a squared b squared. Now what does this mean? This means 4ab cubed. And what does this mean? We took out this stuff, so it's just plus b to the exponent of 4. Now, this is exactly the exact same solution that we solved with that arduous method we found earlier. So utilizing the binomial expansion, we can simplify the expression and our lives a lot quicker. Okay guys, so I'm going to start you off with an easier IB style binomial expansion type question. So what we have here is 2x plus 3 to the exponent of 3. My friend is going to explain how to do something like this, but a bit more challenging a bit later. But first of all, we're going to do this easier example. So how do you solve this with binomial expansion? Well, as we mentioned, binomial expansion can be done through the binomial theorem, which is quite complicated, which we will go onto in a different video, or Pascal's triangle. So Pascal's triangle in this instance, this is equal to n, so we need the third row in Pascal's triangle. So we have 1, 1 and 1, and we have 2, 1, 1, 3, 3, boom, boom, 4, 6, 4, 1, and so this is the 0 row, this is the 1 row, this is the 2 row, and this is the 3 row. So what we're left, essentially, is with these beautiful coefficients here in the third row of Pascal's triangle. These coefficients specifically are 1, 3, 3, and 1. So let me start you off with how to do this. So, what we have is, this is the n, and these are the coefficients. So what we start off with is the first coefficient. This, in this instance, represents our a, as we've mentioned previously, and this represents the b. So, 2x to the exponent of n, which is 3, as we mentioned earlier. This is 3, this is 0, because 3 plus 0 is equal to 3. Now, we continue this process. This can cancel because we're multiplying by the term, and then you get anything to the exponent 0, as we mentioned, is just 1, so these can cancel, and this can cancel. So, bring this down, you get 2x cubed, but you don't get 2x cubed. Haha, I tried to trick you there. That is a common student mistake when they do this, because they do not distribute the exponent 3 to both specific things here. They don't distribute this. So, what you do here is 8 times the exponent of 3, because I distributed it to the 2 as well. Don't forget to do that. Plus 3 times 2 squared, which is 4, x squared, which is another way of saying 12 x squared. Okay, so also this is a little tip. If you find it's complicated to keep track of where you are, just cross out the thing. You don't need to think about it, just cross it out when you're going along, so it's easier to keep track of where you are. So we said this is 12x squared plus 6x, because 3 times 2 is 6, and then just x, times 3 squared, which is 9, so 6 times 9 is 54. So that's 54x. Now, plus 3 cubed, which is the same as saying 27. Okay, so what we have here then is the exponent 3, the exponent 2, the exponent 1, and the exponent 0. And I've written it in this specific order because the IB tend to like when you write your final expressions in descending degree order. And so that is what I have done here in this answer, beautifully written, as we can see here. And that is how to simplify this expression in an IB exam. Let's go. Okay, so this is another example of one of those horrible, well not horrible, but doable IB style questions.
Now you have to go back to remember what I said a second ago. The IB loves, they love to confuse you. You'll recognize they have the same trick they were running in the previous problem. They're only showing us part of factorial here. You'll recognize 10, 11, 10, 9, 8. Where's the rest of it?
Exactly.
Well, who knows?
This whole bit here, the mystery bit of the factorial, is missing. But we, as intelligent intellectuals, know this can be expressed as 11 factorial. And what 11 factorial means is times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. Now, what is this horrible thing here? What does that actually mean? Now, pause the video if you know the answer. This means 7 factorial, okay? 7 factorial. So, what does this horrible thing down here, the denominator, mean? Denominator. What does that mean? Well, this means 4 factorial, okay? That means 4 factorial. So, this denominator means 4 factorial, and as we discovered, this numerator means 11 factorial with a missing 7 factorial. What does this missing 7 factorial actually mean? Well, 11 times 10 times 9 times 8 means that we want to get rid of this because in the actual question it doesn't exist. So how do you get rid of it? You divide. So this means 7 times 6 times 5 times 4 times 3 times 2 times 1 as well. And then this is over 4 times 3 times 2 times 1.
Now let me add a brief explanation here. As we obviously mentioned in our previous problem, just for those who may have missed it, this, if you express this as 11 factorial, right? If we express this right over here as 11 factorial, we can cancel out the 7, 6, 5, 4, 3, 2, 1 with the digit of 7, 6, 5, 4, 3, 2, 1 down here. So right, you can re-express it like this.
Exactly.
If you missed it in the previous problem, go back and watch it.
Exactly. So what this actually means, as mentioned, is 11 times 9 times 8 is 11 factorial over 7 factorial because we are getting rid of this stuff. We're getting rid of that. We don't want it because it doesn't exist in the question. So we're getting rid of it, meaning divide. Now, in the actual question, we see 4 factorial in the denominator. So that remains. We still have a lovely 4 factorial. Boom. Actually, that's misleading because that doesn't show anything. So we had 11 factorial over 7 factorial over 4 factorial. Now, this cannot be expressed beautifully. So how would you rewrite this in a more simplified and mathematically logical manner? Well, this 4, there are 2 denominators here, as you can see. This 4 in the denominator, in the further denominator, shouldn't be another denominator. So what you do is you get 11 factorial over 7 factorial. Now to get rid of that 4 in the denominator, you put it up. So you say times by 4 factorial. Now, we know that when we are getting rid of denominators in a double fraction, we need to do the reciprocal of that. So this is 4 factorial over 1. Okay, but the reciprocal means that we need to switch these 2 things here. Reciprocal means that you switch the numerator with the denominator. So this means that it's now 1 over 4 factorial. So get rid of that. We don't want that. So now you take down this, and you get 11 factorial over 7 times by 1, which is just 11, times 4 factorial. And then this is mildly messy, so I will express this in a neater format. Thus, the answer, this means therefore mathematically, is 11 factorial over 7 factorial times 4 factorial. This is our third example of how to simplify factorials in factorial notation. So, this is the question. Simplify this. Well, we know that n factorial can be re-expressed utilizing the factorial notation form in this form. N times n minus 1 times n minus 2 times n minus 3. Continuing, because in a factorial you're multiplying, and each time you're multiplying, the term is going down by 1.
Until it eventually reaches 1.
Yeah, exactly. As we explained, these are not variables. All these variables actually represent our numbers. For example, this could actually mean 889, 888, 887. It's just going down until you reach 3 times 2 times 1, because that is factorial notation. So, now, onwards. This can be re-expressed as n minus 1, n minus 2, and n minus 3, repeating, because we're going down by 1 each term.
So using his 889 example, this would be 889, this would be 888, 887. Each subsequent term decreases by 1.
Exactly.
Do not be fooled by this.
Exactly. This, although it looks ugly, is not ugly. This just means numbers. It's all just numbers. So, what does this mean? N minus 1 divided by n minus 1 is 1. These cancel. This is 1 as well. This is 1 as well. They all just cancel until you get your original 1 times. So, you get n over 1, which is, in fact, the answer. Therefore, the answer is equal to n. Beautiful.
Okay, on to the next one. So, as we can see, example 4. We have n plus 2 factorial over n factorial. Seems weird, but let's go back to what our idea of a factorial is. A factorial is a number times every subsequent number lower than it until it eventually reaches 1. So like 889 again, times 888, times 887, so on, so forth. Got that? Until it eventually hits 3 times 2 times 1. So then, let's look at n plus 2. Oh wait, it's addition. So what are we going to do? We can rewrite it. N plus 2 times n plus 1 times n minus 1 times n minus 2. Does everyone see how I got that? You do subtract 1 here, subtract 1 again, 1 again, 1 again, so on and so forth. So now, let's do n factorial. That's not hard at all. Let's just do it like this. N times n minus 1 times n minus 2. But wait, we have some common terms here. We have n here, so let's just take out the n's, right? N minus 1, common term 2. N minus 2 here, and that leaves us with n plus 2 times n plus 1 over 1. Well, we can rewrite that. Let's factor this out, come on, because we know how to expand binomials. N squared plus 3n plus 2 is our final answer. Or you likely could be able to express it on an IB exam simply like this. It likely does not matter. Anyhow, I hope that makes sense.
Precisely.
Let's take a try of another problem and actually try using this. Example number 1. Let's take x minus 2 over x to the 5th power. I will give fair warning. This is not an easy question. But let's still give it a shot nonetheless. Let's start with our method here. We need to write out Pascal's triangle. How do we do that? Start with a 1. Go into 2 ones. 2, 1, 1. 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Does everyone see how I got that? Because this right here, this is the row that we want, right? Because if this is the 0 row, 1, 2, 3, 4, 5. Ta-da. So this is the row we want. Everything above this doesn't matter.
Exactly. And so the coefficients we want are 1, 5, 10, 10, 5, and 1.
So now that we've established that what we want and our coefficients, let's get to the problem. 1. we need to write this as 1 times x to the 5th times negative. So keep in mind here, we have two terms. Remember how in our previous A and B example? B here, keep in mind this. Do not make this mistake on the test. B is equal to negative 2 over x. Okay? Because we need to account for this negative symbol. Let's go on. Negative 2 x to the 0 plus 5 times x to the 4th times negative 2 over x. First, onwards, plus 10 times x cubed, right? Because these are decreasing by 1. The A terms are decreasing by 1, B terms are going up by 1. We have negative 2 x squared plus 10 times x squared times negative 2 over x cubed. Okay? So far, so good. Plus, next coefficient 5. Let's do some simplification here. This doesn't matter, this doesn't matter. Out here, this doesn't matter, this doesn't matter. But that's all we can do. Time to start working, right? X to the 5th plus 5 x to the 4th, right? Times negative 2 over x. So let's just quickly do this. Right, everyone see how I got this? That's equal to negative 10 x to the 4th over x. X is negative 10 x cubed. So, we all get how I understand that, right? Everyone understands this? Got it. This term here. We're going to take 10x cubed, and now we're going to square each term here. So this is going to be 4x squared, right? 4 over x squared. Same method with how we did this one. We're going to write it as a fraction. 10x cubed over 1 times 4. 2 and 3 cancel, let's just leave 1. So now it just gives 40x. This term here. Okay, key detail here. Keep in mind that negative 2 cubed is equal to negative 8. Don't make that mistake on a test. I've seen so many kids do it and it's really sad.
And the reason for this is because 3 is in fact an odd number. And so what this means is minus 2 times minus 2 times minus 2 in practice. What you can see is this is just 4. 4 times minus 2, as we know, is minus 8.
Keep that in mind. Don't screw it up on a test. Onwards. Negative 8 over x cubed. Similar method here. So we're going to express this as 10x squared over 1 times 8 over x cubed. This x, cancel this, leaving this x down here. So we're just going to have 80 over x. Cool? Comprende? Nice. Sorry about like the dysfunctional work. This matters, this matters, this matters, and this matters. That's all you gotta know. Now we're on to this term here, okay? Plus 5x times, what's negative 2 to the 4th? Does anyone know? I know. 16. 16 over x to the 4th.
And negative 2 to the 4th is 16, which is positive because, as mentioned earlier, this exponent is even. And so what it means is minus 2 times minus 2 times minus 2 times minus 2, which is 4 times 4, which is 16. Okay?
Got it? So what you guys always got to remember, there's an easy way to remember this. Odd powers can be negative. Anything like the 7th power, 3rd power, 9th power, anything like that. Onwards. 5x times 16. And we're going to pull out our trusty little calculators and find out that x here cancels, right? So we're going to say that this is equal 80. 5x times 80. So now these x's will cancel, right? This gives 3, this gives 0. So now we're going to say that 80 over x cubed. Onwards, we go down. Okay? This term, negative 2 to the 5th, if something you guys all should know, is negative 32. Negative 32 over x to the 5th. Right? So now let's just combine this and write everything nice and neat because currently this right here is kind of hard to see, right? So let's go transfer this thing down so everyone can see this nice and clearly. X to the 5th minus 10x cubed plus 40x plus 80 over x plus 80 over x cubed minus 32 over x to the 5th will be your final answer. As I warned, this is considered to be a pretty difficult IB style question, but it is something that we should all nonetheless be prepared to answer.
Thanks so much for watching this video. Please leave a like and subscribe down below. This would really help us in expanding this channel and doing more videos like this for the future.
If you have any questions, leave them in the comments down below and we'll get back to you as soon as we can.